Have you ever really stopped to think about how a machine learns? Today we're going to go on a little journey, the journey of data, to see exactly how we teach a computer to think.
So, let's start with a fun question. How can a machine, something with no taste buds, no sense of smell, learn to tell the difference between wines? I mean, it sounds like magic, right? But the secret ingredient isn't magic at all. It's something much more tangible: data.
And our whole journey kicks off right here with this table. This is our wine data set. Instead of taste, what the machine sees is a list of 13 chemical properties for every single wine. Things like alcohol content, acidity, even the color. And see that target column over on the right? That's the key. That's the actual wine class we want the machine to figure out how to predict.
Okay, so that brings us to our first big challenge. Here's our mission. How do we train a model to classify wine into one of 3 different types using only these chemical measurements?
Let's break down what we're working with. We've got a data set of 178 different wine samples. For each of those samples, we have those 13 chemical features. And the goal is crystal clear: predict which one of the 3 wine classes each sample belongs to. It's a classic classification problem.
Now, you can't just throw raw data at a machine and expect good results. It's almost never ready for the main event. Kind of like a rookie athlete, It needs a proper training montage, a whole preparation phase to get it in shape before the real learning can even begin.
And wow, this slide really shows you what I mean. On the left, you've got raw data where variables are on wildly different scales. Just imagine trying to compare a value of, say, 100 for magnesium to a value of 1 for color. The model might accidentally think magnesium is 100 times more important. But after preparation, on the right, everything is clean and scaled. Every feature gets a fair shot at contributing to the final decision.
So what's in this training montage? First up, we'd handle any missing data. And hey, lucky for us, our wine data set is complete. Awesome. Next, we'd look for any noise or weird outliers that could throw things off. And then, and this is absolutely crucial, we scale the features. This makes sure that no single measurement can dominate the learning process just because its numbers are bigger.
With our data all prepped and ready to go, we move on to one of my favorite parts, one of the most elegant steps in machine learning: finding the core patterns. This is all about distilling that pure, essential signal from all the background noise. Think about it. We have 13 different chemical features, but are they all equally important? Probably not. Some might be redundant, basically telling us the same thing in different ways, while others could just be noise. So the real question is, how do we zero in on what truly matters for making our prediction?
Well, the answer is this amazing technique called Principal Component Analysis, or PCA for short. The definition here is key. It's a way to shrink our variables down into a new, smaller set of principal components that still hold most of the original information. It's kind of like taking a really long, detailed book and creating a perfect, concise summary that captures all the main plot points.
So we start right here with our original 13 chemical features. This is our full, unabridged book of data.
And after we run it through PCA, bam! We find that we only need 8 of these summary points, these principal components, to capture over 90% of the original story. We just made our problem so much simpler without losing the plot.
So you might be wondering, okay, why 8? How'd you land on that specific number? We use this cool tool called a scree plot. Just look at this. See how those first few components on the left capture a ton of information, a huge amount of the variance? But then it starts to level off. Each new component adds less and less value. We make our cut right there at the elbow, the point where adding more components just isn't worth it anymore.
Okay, our data is clean, it's prepped, it's distilled down to its very essence. It is finally time for the main event: teaching the machine.
In machine learning, you've basically got 2 main paths. On one side, you have supervised learning. This is like learning with a teacher who has an answer key. We have labeled data. In our case, we know the correct wine types, and we teach the model how to get to those right answers. On the other side, you have unsupervised learning. This is more like giving the machine a huge puzzle with no picture on the box and saying, go find the patterns.
So, since we have the correct answers for each wine sample, this is a classic supervised learning problem. We're going to train a model called a random forest classifier. The name sounds cool, right? You can think of it like this. Instead of asking one single expert for their opinion, you're asking a whole forest of expert decision makers for their opinion, and then you just take the majority vote. It's an incredibly powerful method because it relies on collective wisdom.
But how do we train our model and then test it fairly? It's simple, really. You don't give a student the answers to the final exam while they're still studying. So we split our data. We use about 80% of it as a training set to teach the model. The other 20%, we hold that back. It's our unseen testing set, which we'll use to give the model a final exam and see how well it really learned.
And now, the moment of truth. After all that preparation, all that training, did our machine actually pass the test? Oh yeah, a resounding yes. The model hit 92% accuracy on data it had never ever seen before. That means it correctly classified more than 9 out of 10 new wines. That is seriously impressive stuff.
But, 92% is just a headline. For the real story, we look at this, a confusion matrix. It shows us exactly where the model succeeded and where it got, well, confused. Down the side, you have the true wine class. Across the top, you have what our model predicted. Everything on that diagonal line from top left to bottom right, that's a correct answer. Now, anything that's off that diagonal shows us a mistake. We can see precisely where the model got confused between the different classes of wine. And just like the quote says, this shows us exactly where the model is strong and, more importantly, where it can be improved. And that's a level of detail a single accuracy score could never give you.
So, we've successfully built a model that can taste wine. It's amazing. But this is really just the beginning. Where does the journey of machine learning go from here?
What we just walked through are the fundamentals of machine learning. But the field goes so much deeper, into the incredible world of deep learning. This is where you find these super complex models called neural networks, which are actually inspired by the structure of our own brains. And these are the models powering all the advanced AI we see all around us, from self-driving cars and face recognition to real-time language translation.
So, we've seen how data can teach a machine to have a sense of taste. It's a pretty powerful idea, isn't it? And it leaves us with one big question to chew on. If machines can learn to understand our tastes, what do you think they should learn next?